Hey folks, in this video we're going to do a little RL circuit analysis. So first of all, if you need a moment to copy this circuit down, please pause the video now and go ahead and do that. All right, so we have an open switch and the battery is isolated, meaning there's no current flowing anywhere in our circuit right now. And at t equals 0, we're going to close the switch. And one of our goals, the main goal here, is we're going to find all the currents as a function of time. So I'll start off by labeling where the currents are. So we have a current here, and I'll draw that in red. We'll call that current I1. So this is I1. We'll call the current that goes through the inductor I2, and then we'll call this current over here I3. And I3 is going to equal I1 minus I2, looking at this junction right there. Okay. Now, we're going to eventually do some math to get all those currents as functions of time. But before we do that, we're going to look at the beginning and final values of those currents. That you can do without doing a whole lot of math. So we're going to look at I1, I2, and I3. First at t equals 0, the moment we close the switch, and then after a long, long time. Okay, so remember, what does an inductor do? An inductor tries to keep current the same. Well, before we close the switch, I2 is 0. And when you first close the switch, it's going to remain 0. The inductor is going to try to keep it 0. So what does that mean? Okay, what that means is current is only going to flow around the outside loop of our circuit. So what's that current going to be? Well, we have 12 volts and we have a total of 17 ohms in series. So I1 and I3 will both be the same. They'll be 12 over 17 to start with. Okay. In other words, when we close that switch, the current will only flow around the outside. After time goes by, current will flow through the inductor. And after a long, long time, the inductor behaves like a wire. Okay. So what does that look like then? Well, in that case, you have R2 and R3 in parallel. Now, they're 10 ohms each. 1 over 10 plus 1 over 10 is 2 over 10. 1 over 5, which is 5 ohms. So you have that 5 ohms of resistance in series with this 7 ohm resistor. So that's 12 ohms. Okay, so what's 12 volts divided by 12 ohms? Well, it's 1. So I1 will be 1 amp after a long time. When that current gets to here, because R2 and R3 are equal, that current will equally split between R2 and R3, and these will each be a half of an amp. Okay, so there's the starting and final values for our current, okay, for all three of our currents. Now, what about the in-between times? Well, what we're going to do is we're going to eventually solve for I2 first. Once we get I2, the rest of them are pretty easy. And here's what we're going to do. And I've talked about this shortcut before when we talked about RC circuits, and I'll do it again here. So eventually we're going to get a first order differential equation. And the idea is to get it in terms of this. Some constant minus I2 minus some other constant di2 dt equals 0. So instead of doing all the calculus, we're going to get an equation that looks like this. If we get an equation that looks like that, then our current will be I will equal some I naught value, okay, which we already know. That's half an amp. That's what the coefficient in front of there is, okay. But that coefficient is simply going to be A. So when we get this equation here, A should be half when we get it. So we'll see, okay? And then the current's going to go from 0 to a max value. So we want 1 minus E to the negative T over, and then what goes in here? B. Okay, so this is going to be our time constant tau, which we know is L over R. Okay, now be careful here. What R do we use here? Well, we don't know yet. Okay, now I'm going to show you a shortcut for that too later. But for now, we're just going to know that that's going to be tau. It's going to go here. So whatever constant is out front, that goes out front there. And whatever's in front of your di dt, that is in the denominator of the time there. But you got to make sure the equation is such that there's no coefficient in front of I2 there. Okay, so just have a minus sign. All right, so let's do that. Okay, so now we're going to use Kirchhoff's loop rules. Okay, so I'll start with the left-hand loop. So I'm going to start at the switch, and I'm going to work my way clockwise to the left-hand loop. So I'm doing Kirchhoff's loop rule. So we'll call this left loop. Okay, so left loop. So we have an EMF, and I'm going to use numbers here, and I'm going to show you why in a minute. So we have a 12 volts. Minus, we're going with the current through I1, so that's minus 7I1, okay? Then we go with I2 through R2, so that's minus 10I2, and then minus L di dt. L is 0.1, it's 100 millihenries or 0.1 henries, and it's di2 dt. Now, by the way, subscripts here are incredibly important, right? All right, and we're back to the switch, so we say that L equals 0. Well, here's our problem. We have an I1 and I2 in that equation. So then let's do the outer loop. Okay, so our first two terms are identical, 12 minus 7I1. Okay, then we go with I3 through R3. Now, I3 is equal to I1 minus I2, so I'm going to make that substitution right away. All right, so it's going to be minus 10 times I1 minus I2. So minus 10 times I1 minus I2, and that's all equal to 0. Okay, so we'll put some like terms together. 12 minus, we got minus 17I1 plus 10I2 equals 0. We need to get we need to get rid of I1 in our first equation. So I'm going to solve for I1 here. So I1 would equal 12 plus 10I2 over 17. So that's our I1 that I'm now going to plug in right here. Okay. And then we're going to have an equation with just I2 and di2 dt in it. All right, so, and again, we're just doing a lot of algebra, basically. So 12 minus 7 times all this crazy stuff. 12 plus 10I2 minus 17 minus another 10I2 minus 0.1 di2 dt all equals 0. Okay, so then if we multiply all this out and put like terms together, I'll spare you all that crazy algebra. You'll get the following. You'll get 7.06 minus 14.12 I2 minus 0.1 di2 dt equals 0. And I will now divide everything by 14.12 to get I2 without a coefficient in front. So the first term is, hello, it's a half, minus I2. Now, I'm going to rewrite this as minus 0.1 over 14.12 di2 dt, and that equals 0. I'm writing it that way for a reason. Now, I will go ahead and rewrite this minus I2. If you plug this in a calculator, I get 0.00708 approximately di2 dt. Now, there's a reason why I wrote it out the way I did up here, and I'll show you that in a minute. Okay, but now we've got it, okay? We've got this equation in this form. So here's my answer. Now, we've gone through this calculus before, but I'm not going to bother going through it here. We're going to use our little shortcut here for math. All right, so our I2 is equal to the leading coefficient, 1/2, okay, times 1 minus e to the negative t divided by whatever's in front of di2 dt, which is our 0.00708. Okay, so that is I2 as a function of time through this circuit. Notice that it starts when time equals 0, e to the 0 is 1, and so 1 minus 1 is 0. So our I2 starts off at 0, which we said it should. After a long time, e to the negative big number is 0, so this becomes a half, which we said it should. So this equation does follow what we thought it should. Now, having said all that, this 0.00708, that actually comes from somewhere, okay? And here is another super shortcut. Notice that is equal to 0.1 divided by 14.12. Well, 0.1 is L. right? Now we know that tau should be L over R. Well, okay, L is 0.1. 14.12. What is that? What R is that? Well, that's REQ, but you got to be careful. It's not REQ for the battery. The battery is REQ, and what does the battery see? Well, it sees the 7 ohms, and then it sees these two in parallel, which is 5, so that's 12, right? That's not 14.14, right? So where does the 14.14 come from? Well, what's the equivalent resistance that the inductor sees? If the inductor were the primary driver of current, what is the resistance that the inductor sees? Well, the inductor would see, it would, if the inductor were the only thing pushing current, let's say the battery was gone, and the inductor were the only thing pushing current, okay? So current would have to go through R2, right? So that's 10. And then the current could split. It can either go left or it can go right. That means that this 7 ohm resistor and this 10 ohm resistor are in parallel, okay? Well, if you do 1 over 7 plus 1 over 10 and flip it over, you get about 4.14, okay? And then 4.14 plus 10 is 0.12. You get 14.12. So if you have a fairly simple circuit like this where the inductor the current either goes this way or this way for the inductor, well, then you just figure out the REQ for the inductor, and that's the REQ that goes down here. So you could literally write this answer down without even doing all this stuff, without doing all the loops and stuff. Okay, so this is like what I would call a super shortcut. Okay, now once you got I2, you can go back and plug that in to get I1 and I3. So for instance, I1, we got this. So I will save you all the algebra, but if you plug in this in for I2 right there and solve for I1, okay, you will get the following. And if you reduce it and get like terms together, you're going to get 17 minus 5e to the negative t over, I'll just put tau down, but that tau is that 0.00708, or it's 0.1 over 14.12 divided by 17. So that's your I1. Now notice when t equals 0, e to the 0 is 1, you get 17 minus 5, you get 12 over 17. So our current should have been 12 over 17 to start with. Okay, cool. And then after a long time, e to the negative big number is 0, you get 17 over 17, you get 1, which I1 should have been 1 after a long time. You do a similar thing for I3. We know that I3 right there is equal to I1 minus I2. So if you take this minus this, you get like, common denominators, and you carefully subtract and all that stuff. You're going to get the following. And again, I'll spare you all the algebra, but you would get the following. You would get 17 plus 7e to the negative t over tau divided by 34. Okay, so if you got, put like terms together and got common denominator and everything, you get that. Now again, does that do what it's supposed to do? Well, at t equals 0, e to the 0 is 1. You get 17 plus 7. You get 24 over 34, which reduces down to 12 over 17. So I3 should be 12 over 17 to start with. After a long time, e to the negative big number 0, you get 17 over 34, which is a half, which is what we said it should be after a long time. So there's our 3 equations. If you were to graph these currents, okay, so this is current as a function of time. Okay, so you have some asymptotes. You have 1, 12/17 and a half. So I'll put the 1 right there. You got 12/17, about there. And then you got a half, which, I don't know, I'll put it about there. Okay, so let's look at each of these currents. Let's start with I2. I2 starts off at 0 and eventually becomes a half, so it would grow like that, which is still exponential decay, but so that would be I2. Okay, I1 starts off at 12/17, so right there, and that grows to 1. So it looks like that. So that would be I1. I3, oh, and I'm sorry, this down here is supposed to be I3. I apologize for that. Please make that an I3. All right, I3 also starts off at 12/17, but it tends toward a half, like so. Okay, so that's your I3. Now notice, if you were to draw a vertical line anywhere on this graph, I1 plus I3 equals I2 at all times. Okay, so that's always going to be true. Okay, so that's a graphing your currents as functions of time, just graphing these three functions. Okay, the one last thing I'll do for this circuit is, what is the voltage of the inductor as a function of time? Well, let's talk about the beginning and end things first. Okay, when after a long time, the voltage should be zero. The inductor acts like a wire. So whatever function we get, it should be zero after a long time. But what about when you first close the switch? Well, when you first close the switch, no current should flow through here at all. Okay. So the current's going to flow around the outer loop. Okay. And this inductor and resistor are in parallel with this resistor. But since I2 is zero, the voltage across R2 is zero, meaning this voltage of the inductor and this voltage of the resistor have to be equal at the moment you first close the switch. Well, what is the voltage when you first close the switch across R3? Well, it's I3, which is 17/12 times 10. Okay, I3, R3. If you multiply that out, you get about 7.06 volts. Okay, so that's the voltage across R3 when you first close the switch, which should be the voltage across L when you first close the switch. Well, let's double check that. So we know that E is equal to negative L di2 dt. Okay, so E equals negative 0.1 times the derivative of I2. Okay, so what is that? Okay, so I'm taking the derivative of this. So that's a half. So we got a half sitting there. Okay, times 0 minus. So times 0 minus. Okay, and then negative 1 over 0.00, so negative 1 over 0.00708 e to the negative t divided by 0.00708. Okay, so that is your voltage across the inductor, or of the inductor, as a function of time. So let's go ahead and do that. So if you got three negatives there, so you end up with a negative. Okay, I'll talk about that in a second. If you take 0.1 times a half divided by this, you're going to get your 7.06. And then e to the negative t divided by 0.00708, which is our tau. Okay, so that is E as a function of time for the inductor. Now, let's talk about that for a second. Why is it negative? Okay, well, when the current is flowing, the battery makes a positive voltage, and all these voltages are voltage drops. So the charges that are flowing through here, they gain voltage going through the battery, and then they lose voltage when they go through either a resistor or the inductor. So that's why you get that negative value there. Okay, now what we're going to do in this next video is we're going to take this switch and we're going to open it up and see what happens. Okay, so I hope this fairly long video was helpful, and thank you very much.